It'd be pretty cool if I could search the entire periodic table for any word, not just pancakes, and see if I could spell it out with a list of elements. So I thought to myself, yeah, I could do that. So let's start off with these libraries. I got all 118 elements and their atomic numbers at this website. Once I sent in a request to the URL and retrieved the HTML, I used pandas to read the HTML and extract all of the tables. In this case, it returns a list and there is only one table, which is why I looked at the 0th index. I then converted it into a CSV so that I could call it without sending multiple requests to the website science.co. Then I read it into memory and filtered the data frame for what I needed. So now that we have it in memory, I'm going to comment out the code where we sent in a request so that I don't keep running it when we test this out. The only columns we need are 3 and 1, which are the chemical element and atomic number respectively, so I can call that here. This is how you filter a data frame for multiple columns. You use double brackets and then type out the column names within those brackets. Now the reason I'm going from index 1 all the way to the end instead of including index 0 is because if we run this, we can see at index 0 the values are atomic number and symbol, which are redundant. We don't need that, so we can drop that from our data frame. After this, I made a dictionary where the keys are the elements and the values are the atomic numbers. In order to build this, we need to understand our parameters. We know the elements of the periodic table have either 1 or 2 letters, and for this video, I'm not including the 3-letter potential elements, which haven't been successfully synthesized in a lab just yet. So if I type the word pancakes, we have to come up with all single and double letter permutations that follow the order of the letters. So here are all of the letter groupings for pancakes, and I'll show you how to create this in a few seconds. Starting with letters P and A, we have P and then PA. Then we move on to letters A and N. So we have A, then AN, so on and so forth, all the way through the word pancakes. The reason the order matters is because we're trying to spell the word out, and including every possible permutation is a waste of computing power because we won't be able to use the vast majority of them to construct our word. Let's look at the letters P and E for example. Connecting P to E doesn't make any sense because nowhere in pancakes could we use PE to help spell out the word. Now that we have that down, let's write this out. So we have our word pancakes and a list permulist to hold the letter permutations we're looking for. Then we loop through a range equal to the length of the word. This if statement says if we're on the last letter, only append that letter, don't look for anything after it because it won't exist. We then append it to permulist and capitalize it with .upper because single letters in the periodic table are capitalized. If we're not on the last letter, then we'll append the current letter as well as the current letter joined with the next letter. For the combined letters, they will be in title case because 2-letter elements have the first letter capitalized and the second letter in lowercase. So let's run this. So here are all of the letter combinations of pancakes based on what we're looking for, and it does match what we had earlier. However, we can clean this up. Let's check which of these are actual elements by looking for it in the dictionary that we created. I made a list called lmperms, and for each item in permulist, I'm going to try and look it up in our dictionary ldict. If the key exists, then we'll append that element to the new list lmperms. However, if we're thrown a key error because the key isn't in the dictionary, then we'll move on to the next element. So now if we run this, now you can see we were able to get rid of some entries and we're only left with real elements. So this next part is what I call Ratchet Code. It's a brute force attack that will create every permutation of letters using the elements in lmperms. When I first wrote this, it was really ugly, and I tried to approach it with combinatorics and graph theory because I was trying to map out all possible paths based on a set of rules I was able to derive. It was easy to do by hand, but hard to program, so I said, screw it, I'm gonna scrap it and go with brute force instead. At the end of the day, ugly code that gets you what you want is better than pretty code that gets you nothing. Big shout out to Stack Overflow where I found this code and then modified it to fit my needs. So in order to reduce computing time, we don't have to generate every possible permutation. Let's say we can represent our word entirely through 2-letter elements. Then if we have a word with an even number of letters, take the number of letters and divide it by 2 to get the minimum number of 2-letter elements that we could need. If the number of letters is odd, do the same thing but add 1. This if statement right here just checks to see if the word is even or odd. This %sign is a modulus, which means if you divide by 2, will there be a remainder of 0? If the remainder is 0, it's even, and if it's not, it's odd. On the other side of things, we can calculate the max range like so. You'll use the most amount of elements if every letter in the word is represented by a single letter element, so the max range is simply the length of the word. Since we'll be using this as the upper bound of our range, we want to add 1 to the length, otherwise we won't get permutations equal in length to our word. So that defines the range of permutations we're looking for. Then we call chain.fromIterable, and we pass in the list we're using, as well as r. We'll use r to increment through our range that goes from the min range to the max range. This will create every possible permutation of letters according to our range, and for each value of r, we'll be able to stack all of those permutations into one list, thanks to chain.fromIterable. It will take all the permutations for each value of r, and then group it into one list. So now that we have this, we can make this even more efficient. First, we can check, does lmperms have any values? If it's empty, well then there's no reason for us to even continue with this. Then we can check if the first 2 entries of lmperms are actual elements. Since the entries in lmperms are in order, there's no use proceeding if the first letter of the word or the first 2 letters of the word are not elements. So here are those 2 conditions we were talking about, and then we create a new list called winners, of which we'll iterate through each permutation in our function, powerSet. I then turn that into a set and then into a list so I can remove the duplicates and iterate over it. For each permutation, it checks to see that if you join all of the letters and make them lowercase, will it equal our word? If it does, then we can append it to winners. Finally, we can go through our winners list to pull the individual elements from the winning permutations, plug them into our dictionary ldict, and then return the atomic number so we can generate a meme password. This first checks to see if winners is not empty, because if it was, well then we'd be done right here. So this is the for loop. We're going to print out the word, and then for each of the elements within the winning permutation, we're going to plug it into the dictionary and return the atomic numbers. Now, if there are no winners, we'll print out can't find a winning permutation, and then for lmperms, if there's nothing within that, we'll print out no elements exist for our word. Remember, lmperms is the filtered version of permulist that only includes elements. So if it's empty, well then there's no elements for our word. So let's run this and see what we get. So we have our word, the atomic numbers, and the winning permutation, and we did all of this just to make some pancakes, but if you ask me, yeah, it's worth it. Now you can definitely do this with other words like Montana, maybe flak, perhaps Bitcoin. There's 4 combinations of Bitcoin, but it unfortunately doesn't work with everything like meme. I tried adding digital butter to the pancakes, but unfortunately it can't be done with the current periodic table. If you enjoyed this episode, make sure to like, comment, and subscribe, and I'll see you in the next one.